by binary search. You have to walk on the road in powers of 2. So we'll use that idea today in a different problem. Okay, so to recapitulate, we finished this long sequence of ideas to find local minima in a grid. Right, so maybe this image. So ultimately the invariant was that you ensure that in the square border there is an element which here, for example, you can think of it as the point P. There is this point P whose value is smaller than all the elements in the border square, which here is in orange. So when you begin with, in the base case, there is no orange part, there is no element present there. So we can just take the point P to be top left 0, 0 entry. That's the initialization of P. And then in every round, this will be re-evaluated or changed. Right? So it will be updated by whatever is the current certificate of this invariant. So it looks, it sounds complicated, but ultimately the pseudocode fragment is very, very small. You just have to compare 3 elements and update. So take the mid, for example, take the mid column or the mid row respectively, and here we take mid column, then you find the min there, the min is M2, take the neighbors and compare the 2 neighbors M1, M3 with P. That's all. That's the pseudocode fragment which you can implement. And it works fine. It ultimately gives you a 1 cross 1 grid. And that 1 cross 1 grid in the end is the local minimum. So this runs for log n steps, and the time complexity is order n because of this clever sum. Okay, so with these examples, and this last one was quite complicated. So now you have a good idea of how pseudocodes are designed, and maybe with some mistakes in the beginning, but ultimately you correct all the mistakes and you get the correct pseudocode. But then you have to give a formal proof of correctness. Why is it correct? So it gives what you are claiming it gives, and then how much time it takes. Right? So these are the 2 main components you have to work on. And this is generally hard for the students because you don't have this experience. Okay, this needs a lot of practice and experience of identifying the correct invariant, proving, and identifying the correct time complexity. So we'll now, so maybe we can revisit some of the earlier examples. So example 1 was binary search. So this was, we did binary search. So what are the steps in its proof? So the invariant that it has is the array is sorted, and in the array so there is an array A and there is an X that you want to search. So the invariant is in every recursive call, the invariant is that this will pick the left half or the right half where x is. So to pick the unique half, where x can possibly appear. Okay, so the important thing here is that I think the uniqueness is not very important. What is important is the half that you declare that should have x if x is present at all in the array. So the half that you pick, if it doesn't have x in the end, then it means that the array did not have x. Right? So that is the invariant you have to write and prove. In the array A at all. So either it appears there, or if it is not there, then it is not there anywhere else. Right? That is what you have to write clearly. This is what makes it work. So what you prove is that x is in A if and only if x is in one of the two halves. And which one, that it is easy to find. So this is found in order one time. Right, because you just do a comparison with mid and then you decide which way to move. So this is a very simple pseudocode fragment. So I'm not giving the proofs, but you have to give the proofs of this, each of these statements, which should now be trivial for you. And since these are half, since you are going to a half, the array size halves. In each call, which immediately means that there are login steps. So number of calls is less than equal to login, which gives you the theorem that binary search is in login time. Okay, so this is the template that you have to follow in any algorithm or data structure that you design. So this we have already seen in the class. One thing that we have not seen, but it's in the homework, in the theory homework assignment or practice problems. That is the GCD algorithm. So Euclid's GCD. So Euclid's GCD algorithm is perhaps the oldest algorithm known to us. Okay, it's probably the oldest algorithm which is quite complex. It solves a natural number theory problem, but in a very clever way. And the way you implement it right now is exactly the same as it was mentioned before, as it was mentioned thousands of years ago. Okay, so it was already that precise. So you have seen this algorithm many times. So let's write the pseudocode first. So GCD you want to find of integers a and b, and we assume that a is bigger. So what you do is go up to b equal to 0. So if b is not 0, then you try to reduce it. So you reduce it by, what is the main step here? How do you reduce the input instance a comma b? Yes. So, I mean, directly you can see what the invariant of GCD is. Invariant is that GCD of a and b is the same as the GCD of a modulo, so remainder of a by b and b, right? So you flip it. So a comma b is substituted or replaced by b comma a mod b. So we are simply doing a swap here. And maybe this is wrong. So yes. I want E to be bigger. Yeah. So basically A becomes B, new A is old B, and new B is the old A mod B, the remainder. Okay, so A continues to be at least B, but the new B is strictly smaller than the old B, and in magnitude also, not just in sign, but in magnitude, the way you will define remainder A mod B, the magnitude will actually fall. And this continues, this is a while loop, and in the end you just return what? What is the answer? Yeah, so B will become 0, so GCD will then be the current A. So this is the almost the first algorithm that was designed several millennia ago, and it is extremely fast. So it is so fast that you can take A to be thousands of digits, which is that its magnitude, its value is 2 raised to 1000, right? So if you did 2 raised to 1000 iterations, this is again infinite time. So it's impossible, you cannot actually iterate from 1 to A. So what this does is that it only iterates 1 to log A. Okay, so for 2 raised to 1000, it iterates only 1000 times. So it is a surprisingly clever and fast algorithm, and nothing better can be done. So what are the properties here? So the invariant here is that GCD of any two numbers is always equal to the GCD of B and A mod B. Okay, so the way this is proved is this is actually quite general, so you can write GCD of A and let's say QB plus R so in general any number, first one being QB plus R, the GCD of these two is? Yeah, so you can subtract multiples of B from the first one as many as you wish. So here you can subtract Q times. So when you subtract, then you get R comma B, which is the same as B comma R. So that's all. Okay, so just application of this simple formula for GCD, which follows from definition of GCD. So GCD means greatest common divisor of both of A and B, right? So whatever is the greatest for QB plus R and B, it is exactly the same as the greatest for R and B, irrespective of what Q and R are. So just an instantiation of this gives you A comma B equal to B comma A mod B, and then that is what is done. So that's the invariant. So when the second number becomes 0, then you are talking about B comma 0's GCD, right, which is B. So that's the return value. So that's the invariant, and other properties are, which are also very important. That property is that so each step here in the algorithm takes how much time? So you have to basically, you just have to swap, but before swapping, you have to divide and compute the remainder. So that depends on how many bits A and B have, or how big A and B are. Right? So suppose A and B have, or let me say m bits. So suppose A and B are m bits, or there are m digits or m bits, then this A mod B can be calculated in almost linear time, so in m time. Okay, so this is order m. So based on how many digits you have in A, which is the same as saying how big it is. So bigger A is, the more digits it will have. So it is just proportional to the number of digits. It is not proportional to the value, because value is 2 raised to m. Right? So it is only proportional to the number of digits. So how much space is needed to write down the number in the input. So it is just linear time in the input size. So that's the input size also. So linear in the input. So which we can ignore for now. We are more interested in how many rounds there are instead of these arithmetic details. So this is just basic high school arithmetic. You can implement that, compute A mod B. It takes time around proportional to the input size. And the more important thing is that how many number of rounds there are. So what is that? So how many times will this while loop run? So the property is that every 2 rounds, B actually gets halved. Which means that there are only log B rounds. Or iterations. Okay, so the number of times this while loop will run is actually just, it's again linear in the input size and exponentially smaller, logarithmic in the actual value of the number B. So again, if B is around 2 raised to 1000, which is impossibly large to iterate, this will only take 1,000 many iterations. Okay, 1,000 or 2,000 or smaller than that. So have you seen the proof of this? How is this proved?
We construct a set which takes k iterations and we prove that it has a componentized minimum, and then we use induction to prove that that minimum is Fibonacci numbers.
Yeah, so you can use that idea. You can actually connect this, so that is even stronger. This will give you even fewer iterations. So you can use also by using the Fibonacci sequence or recurrence. So without going into those details, one simple observation you can make here is that suppose you represent the remainder between minus b by 2 and plus b by 2. Right? If you just represented the remainder in this half value, immediately in one step, you would get a halving. Okay, so taking a remainder is actually, I mean, the way we take remainder a mod b, the remainder could come out to be b minus 1, which seems that it is reducing slowly. But you will see in 2-3 steps that it actually converges very fast. So in 2 steps, I think this already, you have halved the size of the integer. The value of the integer has been halved, which means that in terms of digits, you are actually, every time you are reducing 1 digit. 1 digit goes away. So this takes only order m iterations, and so that gives you the theorem that GCD is almost linear time. Okay, so you can compute GCD by so Euclid's GCD algorithm that you have seen and you have implemented. That's the fastest algorithm you can think of. Because by definition, it talks about largest or greatest divisor, which could have been anything from 1 to b. So that's a search space of b, right? But this algorithm achieves the solution in only log b, which means that it did not even see all the integers, right? So it somehow magically, it directly goes into the interesting part of the sample space and only finds that answer. It doesn't look at all the numbers from 1 to b.
In each step, the input size also decreases by half.
Yes.
Why won't it be faster?
Why would it be faster than what?
I'm saying that every iteration, the input size also gets decreased.
Yes.
So
It halves, right? So the input, originally the number was 2 raised to m, and you halve, so m times. Okay. Yeah, so these are the steps again. So you saw it for binary search, and very similar thing is happening here also. Both of them are using this halving property. We'll continue to use it in the next, in a new example. Any questions till now? Okay, so now we will design a data structure which is slightly more complicated than an array. Till now you have only seen arrays, at least in this course. Well, in the quiz you also had linked list. So we'll do that maybe in the next class. So data structure, as we have mentioned before, it's just, it organizes data into the memory in a nice way. So this memory can be RAM, but it is usually the hard disk. Because hard disk has such tremendous amount of data that it needs organization even more. Okay, RAM already is very fast. It is like an array, so you can actually go wherever you want in nanoseconds. So that isn't the problem. Hard disk is the real problem because that is not like an array. It's like a linked list. So if you want to go somewhere, then the head actually has to physically move to that location. So which makes it from nanosecond to millisecond. So it makes it 1,000,000 times slower, okay, to access a position. So it's like the difference between array versus linked list. So in SGD, it is more important to organize properly. Such that the following goals are, ideally, the following goals are achieved. So the space has to be compact. So to solve a problem, your data structure should not demand unlimited space. Okay, space should somehow be limited and ideally minimized. Query or update has to be fast. You have to remember that number of queries is huge. So which means that, I mean, you don't want to solve your problem just for few queries. You want to solve it for millions, billions, and trillions of queries. For example, the database that, or the data structure that Google uses, it is designed for unlimited queries. Right? Queries are coming every few milliseconds. So queries are huge. In all these practical problems, the queries you have to assume is huge, which means that there is so much pressure to keep the query very, very fast. Okay, because if you make the query 2 times slower, then for 1,000,000 queries, it will mean that your algorithm is 2,000,000 times slower. So you have to remember that. The cumulative time you want to minimize. And there is an investment in this. So the one-time computation or pre-processing, which we call. So the one-time pre-processing can be slow. But not too slow. Okay, so this one-time pre-processing is usually needed in data structures, as you will realize in the examples. So you have to, so for example, Google again does scan the internet and it maintains some logs and files and it organizes them in a tree and so on, right? So that is a slow process that is not supposed to get over in milliseconds. So that one-time pre-processing requires longer time. You have that time, but you don't have, again, you cannot make it too relaxed. You cannot make, so Google cannot wait for this process to be over in 1 month. Because if this one-time pre-processing is over in 1 month, then after a month, the data will not be the most recent one. Right? Websites and news and everything would have already changed by then. So it can be a day maybe, but it cannot be a month. So that is the scale. So one-time pre-processing can be slow. You don't need milliseconds, but you also cannot make it many days. While the query has to be really in milliseconds, it has to be very fast. Because the queries, you have to handle billions and trillions. And again, the space is, requires money, so that has to be compact. Because all these hard disks and everything requires air conditioning and electricity and all that. So you cannot have You cannot assume that to be unlimited. So these are the big goals. Obviously, in this course, you are not expected to design Google, so you don't have to take stress. But the way we will do complexity analysis, we will try to look at these features asymptotically. Because ultimately, at some point, they are important. So to see this in action, let us take a challenging problem, which has been mentioned before. So this is the question of range minima. So this question was that you are given an array of length n, size n, and query will be of the type I comma j. So when the user asks a query I comma j, then what you have to answer is, in the array from I to j, what is the minimum element? And you have to assume n to be extremely large. So the query here is I comma j, so I is less than equal to j. And the output that you have to give is the minima in this array from I to j in the sys subarray. So thus you cannot assume I and j to be some specific values. They can be anything. I and j go from 0 to n minus 1. Right? Each of them takes n possibilities, so you have n square possibilities of query. So we had this, so we looked at some brute force solutions. So if you want the query time to be order 1, what was the brute force solution? Yeah, then you have to just pre-calculate everything, pre-process and store in a matrix, which is a 2D array. And that has huge problems because the space you are asking is n square. So for n equal to 1 billion, this becomes 10 raised to 18. So space is huge. Bigger problem is that then you put it on a hard disk, and then hard disk, it is not really constant time access. So when you want, let's say, the top corner, it may be fast, but when you want the bottom corner, the head has to move, that will be slow. So it's not really constant time. It will not be milliseconds, for example. It may be much worse. It may again depend on n. So that is not a good solution, because you are putting all the weight on, you are putting all the heavy duty computation on pre-processing. So that becomes too slow. What was the brute force algorithm for linear time query? Yeah, so in linear time query, you don't need any data structure, you just stay with the array. And whenever user asks queries I comma j, you just directly calculate the minimum of I to j in a linear scan. So that will not require any extra space, but then time there is huge because you are essentially doing a full scan of the array in the worst case, right? So we argue everything in the worst case. So that's again a full scan of the array, so it's not a clever algorithm at all. This anybody can do. So those were the old ideas. So brute force either takes order n square space, and query is then order 1 time. Note that the pre-processing is not order n time, or the pre-processing also order n square time. So pre-processing time and space, everything is the maximum possible. It's just the query which is order 1 time. Or it takes, in the other solution, no extra space, so just same as before, order n space. And no pre-processing needed. Query then blows up. It's order n. So which means that the more queries you will make, the more multiples of n you are paying. Right? So that's again, there is no cleverness in that. So these are the only solutions we had seen. So question is that, is there a better solution? So design a data structure to improve this. So to improve this trade-off. So there will always be a trade-off in data structures between how much pre-processing was done, how much space is required, and how much is the query time. Right? You cannot optimize everything simultaneously. That will be too good to be true. So there will always be some trade-off. But is there a trade-off which is better than this? Okay, so that it's implementable in practice. So for this, we will use 2 ideas. So one is the idea that we used in max sum subarray, right? So instead of working with 2 indices, we focused on only one index, which was j. So that is one idea. The second idea was in the quiz, right? When you have to walk on the road to get to your friend, that idea also we'll use here. So like max sum subarray solution, so we can focus on just one subscript, one index. Say now we call it I. So what did we do in max sum subarray? We focused on j and we calculated this array s of j. The array s which will store the value s of j, which meant, which basically stored what is the maximum subarray ending at j. Right, so we can try a similar, we can try with that idea here, start with that idea. But it doesn't seem to help directly. We can't think of an array here which behaves or which gives us the advantages that S gave us there, the array S, because you have to design an array which stores at the ith value, let's say S of I, that has to be the minimum from I to j. But you don't want to use j, so you want to avoid j, so you have to say minimum of, the subarray starting from I to some point. But we don't know which point is helpful, right? This doesn't fit. So how do we, or what do we do with j's now? So they are still, it seems we have to work with all these order n j's. There is no way to just forget or abstract out j, okay, because the the whole question is that the query can be with any j. So I to j, you have to find the minima. When you go from j to j plus 1, the minima may completely change. And when you go from j to, let's say, 2j, it may change like in a completely arbitrary way that you can't keep track of. But anyways, we'll stay with this one point that let's keep I as our primary index and try to somehow subdue j, since we need to account for every j in the query. So if we just went over all the j's, then it again will go into this order n square. So this is still taking n times order n kind of space and time. Right, we have not gotten out of that curse. So now at this point you should remember what you did in the quiz, question 6. So how do you think we should now work with j? Keeping I as the primary index, which j's are important? Yeah, so your immediate answer should be just look at j as powers of 2. Okay, that's a significantly fewer j's than all the j's. Now, why will it work? That you have to ask the student. That I don't know. Right? That we have to try this idea. But that is one thing that the quiz tells you, that well, looking at powers of 2 can be good. So consider going over j's that are powers of 2. So they are only log n many. Right, so this will be a much shorter data structure than storing all the j's for a given I. So what this, how the way, the starting point or main reason why this could help is you have now at least some markers for j. What you have to now check, and that will help you in designing the pseudocode, or even the data structure is kind of now fixed. We have decided that for I 0 to n minus 1, we will only store those j's which are powers of 2. So that is our data structure. So let's call this tiny data structure. So tiny data structure which we are proposing is a new, just like in that max sum subarray problem we had array S, here we'll have an array, now we'll have an array B which is 2-dimensional, so it goes from 0 to n minus 1, that's I, and 2 raised to 0, 2 raised to 1 and so on, powers of 2, so that's exponent is k. So Bik will basically store the minimum of I plus 1, I plus 2 raised to k. Okay, so this is basically a walk only up to power of 2 raised to k, that many steps. So from I you walk for 2 raised to k many or 2 raised to k plus 1 many steps, and whatever is the minima that you report and store in BIK. Okay, so this is a two-dimensional modification, adaptation in fact, of that S array we had before, S of I or S of J we had there. Now here we have B of I, but then we are storing more things. But this more is still quite small. It's only, K can only go up to log n. So it stores that, those minima for all I going from 0 to n minus 1 and k going up to log n. Yeah, this is a very, well, it's not a sparse matrix, it's just a small matrix. It has few columns. Sparse matrix is a technical term that means that many entries are 0. Yeah, but in the n cross n grid, this is a sparse matrix. But we are ignoring that part. We are only, the array is just, as I've written, the range of k is exactly 0 to log n. So it's an n cross log n matrix. So B is n cross log n matrix or 2D array. Yeah, so this is still significantly smaller space requirement than n square. Okay, this is only n log n, so it's almost linear. It is not much bigger than what your input was, the array A. Yeah, so this is just a proposal. I mean, we have not really worked out anything here. We have just decided that we'll store these J's. We'll store these, I mean, store as in we are already pre-processing the answers of these I comma j. But these are special j. It's not all j. So these are j's such that j minus I is 2 raised to k. Okay, we are only looking at those solutions. We can write that down. So it's like looking at the solutions of j minus I equal to 2 raised to k. So you go over all these ijk's. That gives you the matrix B, which is in fact our data structure design. So now the things that remain, the j's that remain that are not in this, let's say j prime, the point is that those answers, the queries I comma j prime, you have to investigate now, are those I comma j prime answers or queries independent of what you have stored? Or is there a dependence? So if there is a dependence, then can you use this data to answer random queries? Log n? Yeah, but it's fine. We don't make it so specific. So yeah, it's true that the array will just get truncated at n minus 1. So whatever, if you cross the border, then you don't have anything. That is the implementation check. So yeah, that is, I think we'll not finish this today. So you should just think about the question of, once I have given you the design of the data structure, what you have to think is an arbitrary query I comma j prime related to I comma j's, where this j minus I is a 2 power. Okay, so the user will be giving arbitrary queries. The user will not respect your array or matrix B. So if the user asks something from matrix B, you will immediately report in constant time. But if the user asks a query of this I comma j prime type, where I comma j prime doesn't respect j prime minus I equal to 2 power, then you have to somehow calculate that on the spot using the matrix B. So how can you do this? Is there any relationship or is this totally independent? So we'll finish it tomorrow.